Now, when we look at the properties of casting, we look at different factors that affects the properties of the casting. It's the dendrites, inclusion, porosity, and shrinkage. Um, Dendrites are how the dendrites are formed. It causes the homogenization, different structure at the outer layer, and the structure, the properties, the strength, mechanical properties at the inside is going to be different. So different surface properties and the bulk properties are kind of not same. Inclusion is when you are pouring, maybe if you're doing the sand casting, maybe an outside element, or maybe an organic element, maybe a piece of wood or piece of sand actually fell into the casting. Now that will act as a stress zone later on. It will damage the mechanical properties of the casting as well. Porosity is when you're pouring too quickly and the air bubbles might get entrapped. So this is why we use like ultrasound sonic vibrators, where they actually kind of vibrates and emits, get rid of all the air bubbles and all the porosity. When I talk about porosity, they are very tiny, teeny air bubbles, micro voids or voids. Other one is shrinkage. Shrinkage happens in a casting when the mold that designed does not compile with the rate of heat transfer. So there's a sudden um, rate of heat transfer. You pour the liquid in, and you haven't given enough shrinkage tolerance, which means there's a runner and the risers. Yeah, anyone? Yeah. There's a runner and the risers. I will show you in a minute. Um, which actually is there to make sure you are providing the shrinkage allowance in inside the for the material. All these defects will negatively affect the mechanical properties of the casting. Okay. So what we do is we, after casting, we do check the whole process and see if the material is fit for purpose. We do not lot of destructive and lot of non-destructive testing. Okay. Now, if you have a look at the forging, what is forging? Now, forging, you have a hot metal and you actually apply a lot of force, and you keep doing that one until you reach the required shape. Just quickly going to show you the video of the forging. So a term known as grain flow. What is a grain flow? Grain flow is a direction orientation of the grains. As you can see in this one, you can see the direction of the grains are in upward direction here. Direction of the grain is in this direction here. Now, this actually gives you enhanced properties. This is one of the reasons the forged products are expensive, more stronger than the non-forged product or die-cast product. Um, Individual grains are elongated in the direction of the applied force because the grains are forming and you're actually just compressing it, you're applying a compression force, uh, and they are actually molding the grains in the direction of the metal, and that gives more and higher strength. Grain flow occurs to some extent in all metal forming process, not just forging, but in forging is a lot more clear, a lot more smoother because the metal is still at high temperature and you can just work and adjust the grain boundaries and the grains. Okay. Now in the there is a term known as isotropic and anisotropic properties. Isotropic properties are the properties that depends on the direction. So, for example, you might have seen the karate chop, the person who just chop the wood into half. Well, it has to do with the grain structure of the wood. Now, if you look at your table, you can see the grains are aligned in this direction. Yeah. Imagine that's the wood, real wood. Now, if you try to break it that way, if that's a table, that way it's much easier. But if you try to do it 90 degree to the direction of the grain, it's very hard. So this table, it's difficult to break in this direction as compared to in that direction. Well, I know it's not real wood, but imagine these are the real grains. Okay. Now, there are certain properties that are affected, which is impact, toughness, ductility, fatigue strength, uh, and one of the fatigue is the ability of the material to withstand a continuous load and over a period of time. It takes years for the crack to develop, a tiny crack, but then it takes a second for this crack to propagate. So we try to avoid fatigue failures. Um, we can improve these properties by either making something out of one single grain, that there is no grain boundaries, no microstructure, or we can align them in a direction that where we think the failure is going to occur. Now, then there is a thing called principal stress. For example, if I am standing on the table, the principal stress is in horizontal direction. So there is a principal stress because if you're standing on the table, the stress is acting downward. This is the kind of stress you're trying to avoid. That's known as principal stress. So which means I have to make the legs of the table a lot stronger. So maybe I can orient the grain in such a way that I can align that in that specific direction. So table can be stronger in the direction where I want to be. The wings of the aeroplane is stronger in one direction, not in other direction, because it's taking the load in this direction. It's not taking the load across that direction. So we can achieve the directional properties, unidirectional properties. And why would you like to do that? To save material, to save the weight, and so on. Why do we do the forging, and what are the advantages of forging? The forging, uh, one of the main advantage of forging is it can refine the grain structure, it can redefine the grain structure. Forging is a lot better to casting, it's a lot better to machining, because the natural grain of the metal, it's in flow, it just settles in all different directions, it flows with the shape, which gives extra strength. Now, casting has an isotropic grain structure. We discussed what the isotropic is. Um, and it might be strong in only one direction, but not in the multiple direction. Now, the structural reliability of forging mean if something is forged, it can withstand the load in X and the Y and in the Z direction. So it's give you extra surety and the factor of safety. And also it provides more uniform response to heat treatment and machining operation as well. Now this process is known as rolling process. In rolling process, you have two metals and you just roll the metals through a rolling. Now these are hot rolling and cold rolling. Imagine we got a wrought product with a large grain structure and you pass it to the rolls, and the rolls, when imagine it's a hot rolling we're doing, which mean the workpiece we are entering into the roll, it's hot, and the grain boundaries, the grain structure will be aligned. But now there's a thing called new grain formation or recrystallization. Recrystallization is a process where the deformed grain structures form into a new grain structure, and these new grain structure grows, and you actually see these grains and that grain, they look pretty much same but smaller size. And this whole process is known as, from here after the pass to that one, is known as recrystallization process. How does it affect the bigger grain and the smaller grain? How does it affect the properties of the metal? If the grain size is big, they are more ductile. If the grain size is small, they are more brittle. If the grain size is big, there's a it's more fatigue resistance. If the grain size is small, they are less fatigue resistance. The grain boundaries are the area of the impurities. So these are kind of the, if you look at one grain, the middle of the grain is going to be more pure as compared to you move away from the grain, center of the grain. And all the impurities are actually at the grain boundaries. The grain boundaries, which are these lines are brittle. Most of the failure that actually happens at the grain boundary. So why we can't have something that made of one certain grain, just one grain? There's a process. It's called a single grain growth, and we do for wind turbines and the other high performance equipment. We need that one. So I will explain that later on. Now we got a property known as isotropic or anisotropic structure. Now, anisotropic is a property of being directionally dependent, which mean the different properties in different direction. Um, Imagine a ruler. For example, if you are able to bend it, let me just show you. Um, if I apply a load of, let's say, 10 Newton, I can bend in this direction. But let me apply a load of 10 Newton. I can't bend it now in this direction. Yeah. So these are anisotropic properties. Yeah. The physical and mechanical properties will also always be different. Yeah. So I will explain that in more detail later on. This is a microstructure of cold drawn steel. This is the undrawn microstructure. You can actually see the lines going in that direction. I'm not sure if that's obvious. This is a microstructure of a cold drawn steel. This is an undrawn one. You can actually see that there are lines across this one, like around 50-degree angle. I'm not able to see on the second pass, but on the first pass, this is at 10 micrometer, by the way, this length from here to here. I can see it's been drawn in this side. So from this side towards that one. And this is the third pass. It's look like it's around that angle, 45, 50-degree angle. So you can see the grain structures, microstructure at 3 different levels. Okay. Now the next thing is recrystallization. If you apply a heat like hot working, it will cause the grain to disorient. It will absorb the energy and it won't to give away that energy, because everything wants to achieve a stable state, which is a lower energy state. Now it want to go back to original undistorted structure. Now when you're doing the rolling, you are actually disorienting the grain structure, but later on the whole recrystallization process will occur where it go back to kind of, or try to go back to original structure. Sometimes it succeeds, sometimes it doesn't. The grain might be smaller, but it will be like equi-x grain, like distributed evenly, same size all across. And this usually happen in hot working a lot as compared to cold working. Now, how does the property effect of temperature on the material properties? If you have a look at the first one, there's a thing called residual stresses. Whenever you use the hot working or cold working on a product metal, there are some stresses that are left inside the material. If you do a cold working, what will actually happen is a lot of stresses are left into that one. Residual stresses, uh, over a period of time, if you increase the temperature, residual stresses actually kind of decreases. If you increase the temperature, the ductility actually increases. If you increase the temperature, the hardness actually decreases, and it's linked to the grain structure. Here you can see small grain structures, yeah, recrystallization happening, and the big grain structures.